Most of the natural substances that we see around us are mixtures. The air we breathe, the fabrics that we wear, the coal that you burn in your furnace, as well as the gasoline in your automobile, are mixtures of many things. But as you know, these substances are all made up of a limited number of elements, about 100 in all, that are shown on this chart. Some of these are very familiar to you. For example, oxygen, sulfur, carbon, aluminum, and copper. But these elements like to react with each other, and so they are generally not found free in nature. For example, iron occurs in many different compounds, such as the oxide, which is a nice red powder, or it occurs as a sulfide. This is very impure, looks very much like coal. But then there's also this other sulfide, which occurs sometimes in very nice specimens, such as this. This is called pyrite. Note the golden, glistening surfaces. Of course, you wouldn't find those nice pieces very often, but you might find these broken chunks, and if you saw them among a lot of black rocks, you'd be really quite surprised by it. Aluminum, like iron, occurs in many different forms. The pure oxide is a nice white powder, but that is not the way in which you would find it free in nature. I have here some natural aluminum oxide, or bauxite, as it is mined and used industrially. Now, such names as bauxite, or pyrite, or salt, or sand, the common names of substances, give you no clue in regard to the chemical composition. But the chemical names, such as aluminum oxide, or iron sulfide, or sodium chloride, do tell you something about this composition. Furthermore, the chemical names were chosen to tell you whether the substance is an element or a compound. For example, copper, iodine, oxygen, carbon are obviously elements. But aluminum oxide, or iron sulfide, or sodium chloride are compounds. Now, these natural substances which we have here are obviously quite impure. And to get the pure material out of them, we must use some kind of sorting process. For example, I could pick out the pure crystals of iron sulfide out of this, but that would be a rather tedious and long job. In the case of bauxite, I can dissolve the aluminum oxide and separate it from its impurities, and that's the way it's done industrially. But now, how do we identify a substance after we have it separated? Well, the identity of a substance is indicated by its characteristic properties, its melting point, or boiling point, or solubility, or its color, or hardness, or any of a number of such properties. And when the substance is really pure, these properties are very sharp and exact, just as the freezing point of pure water is exactly at 0 degrees. Now, these properties can also be used to distinguish substances that are otherwise somewhat alike. For example, this mineral, pyrite, sometimes called fool's gold because of its golden color and its shiny surfaces, would not be mistaken for real gold if we simply measure its density. Although it is fairly heavy, it is still not as heavy as gold. Let me show you. I have here a small nugget of pure gold, and here a chunk of pyrite that weighs just about the same amount. Let me show you here on the balance. We'll put the gold on that pan and the piece of pyrite on this one, and you see they weigh approximately the same. But although the pyrite is at least 3 times as large as the piece of gold, so its density must be only about 1/3 as great. Now let me show you something else. I'll put this gold piece on the anvil and give it a few real hard blows. You see it doesn't break, it only flattens, and indicating that it is a malleable metal. Let's do the same thing now with the pyrite. You You see, it is very brittle and flies to 1,000 pieces. Not all of the tests for physical properties of substances are as simple or as obvious as these tests. But I think it is clear that every substance, whether it be an element like the gold or a compound like the iron sulfide, does have a set of characteristic properties by which it is recognized. Furthermore, the compound has properties that are quite different from those of the elements of which it is made. Let me show you this with a little chemistry. I'm going to make a compound out of two elements, and then later on we will take the compound apart again. The elements we will use are copper. In this case we will use copper turnings, and it has its characteristic copper color and its flexibility, and it's also characterized by its good electrical conductivity. And the sulfur is a nice yellow powder of crystalline nature, but it's not easy to see the crystalline quality of the sulfur here, so I have taken some and melted it in a test tube and let it solidify so that you can see the nice crystals. Now, sulfur is also characterized by its easy solubility in carbon bisulfide. And we'll show that. We merely dump the sulfur in this test tube and add some carbon bisulfide to it. And then shake it up for a minute to give it a chance to dissolve. But we don't have to wait for it all to dissolve. We can pour it through this filter to remove the undissolved sulfur and let some of the clear liquid collect on this watch glass. When we have a little of it there, we will simply put it on this warm, hot plate and let it evaporate so that you can see the nice crystals. This picture is speeded up so that each second represents a minute. Now there, the first crystals are forming. Now these crystals will have the characteristic properties of sulfur. They will have the sharp melting point, boiling point, and the density and color that sulfur should have. In fact, I can take these same crystals and dissolve them again in carbon bisulfide, and by evaporating the solution as we've done here, I can get the crystals back a second time. And they will again have the same properties as before. In fact, I can do that any number of times, and I'll always get back the same sulfur with the same characteristic properties. Now, this is characteristic of a pure substance. But now mixtures are different. Let me show you. I have here some copper chips, the same metal that we have used before, and I will mix some sulfur with it. It doesn't really matter how much sulfur I put in when I make a mixture. You see, I have a mixture of copper and sulfur. I could add a little more if I like, because the proportions are not important in making a mixture. Now, as you readily understand, I could take this mixture apart quite easily. I could either pick the pieces of copper out, or, a little more simply, I could pour some of it on this screen, and by stirring it around, I could make the sulfur go through the wire screen and leave the copper on top. And so we have separated the two. A little more elegant method might be to use the process we have used before with carbon bisulfide. So we pour the carbon bisulfide on the mixture, shake it around a little bit to give the sulfur a chance to dissolve, and then pour the solution on the watch glass, and stand it on the warm plate and let the solvent evaporate. And again, we'll get back the pure sulfur crystals. And here once more, by slowing the camera, we have speeded up the action. Now, it is characteristic of mixtures that they can be separated by such simple means as this. Now let us make a compound. I'll make the compound out of the same two elements we've been using here by using sulfur and copper, this time in measured amounts. I'll pour the sulfur in the tube and then stuff the copper in on top of it. I'm putting in just the right amount of copper to combine with the sulfur in the proportions in which nature makes these elements combine. Now, I don't really have a mixture here because the sulfur is all in the bottom. But that doesn't matter because to make them combine, I have to heat them. And when I do that, the sulfur will boil up on the copper. We'll adjust the flame to get a good hot fire. And of course, if it's going to get hot, I'd better put it in this, hold it in this clamp. And I'll warm the tube up gently so it won't crack from too sudden heating. Then apply the heat to the bottom. Now you see the sulfur is melting, changing color, and it's beginning to vaporize. And it's distilling up on the copper. Now you see the reaction's beginning. See that red glow? And as the sulfur distills higher and higher, it combines with the copper to form copper sulfide, a compound. We will heat this until the sulfur has had a chance to react with all of the copper. Now that humming sound is just the vibration of the hot sulfur vapor in the tube. And you notice the copper has all reacted. So we did use both elements in the exact proportions in which they naturally combine. This evolution of heat indicates that a chemical reaction may have taken place. If a chemical reaction has occurred, we should have a new compound with its own characteristic physical properties. In fact, we suspect that we will have copper sulfide since we made it out of copper and sulfur. But now let's see what we have. I'll dig the stuff loose, see if I can extract the sulfur out of it. So I'll put a little of it back in the test tube and use the same procedure that we used before, dissolving the sulfur, if there's any there, in carbon bisulfide. And after shaking it around to give the sulfur a chance to dissolve, we'll just pour the solution off on this watch glass and put it on the hot plate to evaporate. And if it has extracted any sulfur out of this, it should appear on the watch glass. Now the carbon bisulfide has evaporated, but there are no sulfur crystals left. This indicates that the carbon disulfide was unable to extract the sulfur from our product. This product is different from either the copper or the sulfur from which it was made. It is a compound, copper sulfide, and has its own characteristic physical properties. Its color, its brittleness, its melting point, and so forth. But we can take it apart if we use chemical reactions. Then the cycle will be complete, for we started with two elements, copper and sulfur, and we made a mixture. Then we combined them to form a compound, and now we will take them apart again. To do this, I'm going to heat the product in a stream of oxygen to convert it into two oxides. So let's put this in the boat. And then put the boat in this glass tube furnace. And now we will turn on the oxygen. Now the oxygen will come through this bubbler, which only serves to tell us how fast it's flowing. It will pass down over the sample, where it will be heated and will react, and the products of combustion will pass on through the furnace and through this dust trap and down into the cold trap which we have here, cooled by means of dry ice and acetone. I'll wipe this off so you can see it frost up. The temperature is about 80 degrees below zero. And the products of combustion from our sample coming in here will freeze out and stay there so that we can examine them later. Now let's light the burner and get the reaction going. And here again, we are using time-lapse photography. Now this oxidation actually required about half an hour. I believe the reaction is complete now, so I'll shut off the burner and let the furnace cool. While it is cooling, let's examine the trap and see what we've made. There you see we have a nice white solid. And that's very cold. Now it's beginning to melt a little bit. There's a little bit of liquid in there. So while it is melting, while we have the equilibrium between the solid and the liquid phases, let's put in a thermometer and determine the melting point. I'll have to wipe off the frost on the top so we can read the thermometer. It's going down. You can now see both the liquid and the solid. And the temperature is just about 75, below zero centigrade. Now we can also determine the boiling point in this same apparatus. I can warm up the material better with this beaker of water. Now it's beginning to boil. Bubbles are rising quite nicely. And the temperature is just about 10 degrees below zero. Now those are the melting point and the boiling point of sulfur dioxide. I can smell it too. But now how can we be sure? An easy way of doing that would be to put sulfur in the boat in place of the copper sulfide and burn it in a stream of oxygen and let the sulfur dioxide that is formed go through the filter and into the trap and freeze out there. Then we can determine its freezing point and boiling point and see if it is the same as what we got when we burned the copper sulfide. Now let's test the product to see if we've made the same compound. There, we have both liquid and solid in equilibrium, so let's read the melting point. Well, it's just the same as we had before. And this sulfur dioxide is boiling away nicely now, and the thermometer is reading just 10 degrees below 0 centigrade. So the boiling point of this sulfur dioxide is the same as what we obtained before. In fact, both the boiling point and the freezing point of pure sulfur dioxide agree perfectly with the boiling point and freezing point of the sulfur dioxide we made out of our copper sulfide. Now, we did not get free sulfur out of the copper sulfide. We got sulfur dioxide instead. But I think you will understand that we really did get the sulfur out of it. This indirect kind of evidence is often used in the study of chemical compounds. Now, what do we have left of the old product? Well, here it is. We know some sulfur's gone, and we suspect that this is now copper oxide. And it looks like copper oxide. It's black powder, like the bottom of an old copper kettle that's been left on the stove too long. Now, if this is really copper oxide, we can easily take the oxygen out of it by heating it in a stream of hydrogen. And for that, we can use the same apparatus we've used before. So let's put it back in the furnace. We'll first take the boat out in which we have heated the sulfur and put our old product back in again. And now this time, we must not use oxygen, but use hydrogen instead. Now, you know that hydrogen mixed with air is a pretty dangerous mixture, so I'd better change my glasses and put on these safety glasses. And we'll allow a little time to let the hydrogen sweep the air out. Now, we expect the hydrogen is going to react with the copper oxide and form water as a volatile product. And to condense water, we don't need such a cold trap as this, so we'll take it away and just use ice water here. Now put in a new, clean, dry trap and an ordinary mercury thermometer. Connect it up to the tube furnace, and now things are all set. Now I imagine the hydrogen has blown most of the air out, so we can light the burner and get the reaction going. The reaction you see here in 20 seconds actually required 20 minutes. Now let's see what we have. Well, we have a nice clear liquid, which certainly looks like water. But to be sure, we must determine its physical properties. And let's start by measuring the boiling point. So we'll heat it up over the Bunsen burner, but it's going to get kind of hot up here, so I'd better put on a clamp. Now it's warming up, and the temperature is about 30 degrees. Now it's up to 60. Now you can see it's beginning to boil. Now it's boiling away nicely, and the thermometer is reading right at 100 degrees centigrade, which, as you know, is the boiling point of pure water. But now, to be doubly sure, let's measure the freezing point. And I'd better cool this down a little bit in this beaker of water, because I'm going to have to freeze the liquid in the trap with dry ice. And if I put it in suddenly into the dry ice, it's apt to crack the trap. Well, that's just a drop of water on the bottom of the trap falling off into the dry ice. Well, the thermometer's dropping pretty fast. It's down to 40 degrees already. We can be sure that it's all frozen. Now it's slightly below zero. Well, look at there. It's all nice and solid. But we must warm it up a little bit until we have a little liquid as well as solid present. Because the true freezing point of a liquid is the temperature at which you have both liquid and solid together. Now there's a little liquid beginning to form, and the thermometer is right at 0 degrees. So both the freezing point and the boiling point of this liquid agree with the freezing point and boiling point of pure water. So I think we can be pretty sure that this is water. In fact, I'm so sure that I'm willing to take a taste of it. Yes, that's water, all right. Now the furnace should be cool enough so that we can examine the boat. Now there we have a nice red solid. Has the same red color as copper. But to be real sure that this is copper, let's measure its electrical conductivity. These chunks show good conductivity, just like the copper that we started with. And we see that it's copper colored all the way through. Now it ought to be malleable also, like copper. And you see it does flatten out pretty well. But of course it isn't to be expected to be as malleable as copper wire, because this has not been brought up to the melting point. To make no mistake, there are of course many other tests that we could run to prove that this is really copper. But I think the simple tests that we made should be enough to convince you. So now, let's summarize all that we have done in the language of chemistry. The first thing we did was to prepare a mixture of two elements, copper and sulfur. The proportions in which we put them together was not important, and also we could take them apart again by very simple mechanical methods. Next, we combined them to form a new compound, copper sulfide. In this compound, the proportions are exact, and also the physical properties of this new compound are very different from those of the sulfur or the copper of which it is made. Then we took the copper sulfide and oxidized it in a stream of oxygen to make two new compounds, copper oxide and sulfur dioxide. The sulfur dioxide we identified by its characteristic properties, its sharp melting point, its sharp boiling point, and also its very choking odor. The copper oxide was recognized by its color, but more importantly, by the next reaction, in which we heated it in hydrogen to take away the oxygen and give us back again pure copper and water as a byproduct. The water was recognized by its sharp freezing point at 0 degrees centigrade and its sharp boiling point at 100 degrees, and also by its taste. The copper was recognized by its red color, its malleability, and also its good electrical conductivity. And this copper is exactly the same copper that we started with.